Okay, to continue our next stage in our drawing of modulus functions on graphs, we're going to look at a couple of harder examples. And we're also going to look at the other main case of when we need to draw these things. So all of the ones we've looked at so far looked something like this, where everything on the right-hand side was in a modulus function. But this is not always the case. This case here is when the entire function is within a modulus. Everything is within it. But if we remember from our transformations, this isn't the only opportunity. This isn't the only option, rather. Sometimes we can have a system where only the x coordinates are modulus, or the x values within the function are modulus, and not the whole thing. So the difference between these is, let's take a y equals x squared plus 2x plus 1. That's f of x. The first case that we've looked at so far, the modulus of all of f of x, is just the same as the entire thing modulated. If we were to plot this on a graph, well, we already know we would plot whatever is inside, and then we'd reflect anything below the x-axis above it. Yeah, as we've seen before. But if instead of that we have just the x values being modulated, still not sure if that's a word, we'll go with it. Then instead of it all being inside the modulus, it will only be the x values. And this looks a lot different when we actually try and plot it. And we'll see how in a second. Okay, so we've now got our function as before, with only the x values being modulated. So, how would I plot this? Well, my previous video, I talked about, in my opinion, the easiest way to do it, which is splitting it up into the bare essentials, adding one transformation, one layer at a time, and you end up building out a graph over a couple of sketches. But with this kind of graph, that's not as easy to do. The reason for that is because it has more than one x variable. A lot of the time you will only get one x variable, so the examples we looked at last time, but if we end up with more than one x variable in our equation, that becomes tricky. We can't just draw a y equals x graph and then manipulate it like this. We technically could, but that's way above our pay grade. We don't want to bother with any of that. So because of that, when you get a graph that looks like this, what we first want to do is consider it without any modulo to begin with. So f of x equals x squared plus 2x plus 1. Just remove all the modulus functions and just worry about it like this. Now, typically, this will be a function that we recognize. Maybe it will be a quadratic like this, maybe it'll be a sine or a cos or something that we recognize. So what we want to go ahead and do is plot this onto a graph. So x squared plus 2x plus 1, well, we can factorize that, we can find the turning points, etc., etc., etc. And once we do that, we will end up seeing that it looks something like this. This is our x squared plus 2x plus 1 graph. Feel free to pause and check that and derive it yourself, but this is what it looks like. Now we need to ask ourselves, what is actually happening in here? So we know we're forcing all of the x values to be positive. So the instinct is to say, okay, well, I can eliminate everything on this side of the graph. I can just keep this little tick here, and then all my x values are positive. But as we saw earlier when we were solving these equations, that's not always the case. When we were solving equations like this, we know that if we want to solve this for, say, equal to 0, then we would do it twice. We would do it once where my x coordinates are positive and once where they are negative. And I would end up with two different results. Again, we saw that earlier. And because we have these two different results, we can't just rely on the fact our graph is solely going to be placed in this section. But what it does do, and this is a nice way of thinking about it, is it prioritizes this section. Because all over here, my x is positive, and that's what my modulus wants, that's what we're going to start with. So, once we've sketched up this graph, we're going to have a look at what part of this graph is on my positive x side. And I would advise redrawing this rather than rubbing things out if you're using pencil, but I'm just going to rub things out here for ease. And I'm going to either redraw it or just delete the parts of my graph that are not in the positive x section. Once I've done this, all I need to do is reflect this line back across the y-axis. That's all I need to do. Once again, the reason for that is I know that my priority, my first port of call is that all x must be positive. But because of what we saw earlier, where we can technically have some variation, we do need to account for that. The way that we account for that is by reflecting it, and it will look something like that. A key feature of these graphs is we tend to end up having this weird little dip, this kind of bobble that can sometimes look like that. It's quite small, but it can sometimes look like that in our graphs. And this is very normal because in general, it's not going to be smooth. It's going to look like it comes to an abrupt stop and then keeps going again. But this, in essence, is how we draw a graph that looks like this. Now, I want to take a look at some examples using trig. Okay, I'm going to start off with some basic sine examples. Well, I say basic, they're a bit weird, but they are the most basic type of trig questions you can get on this. So, on the left, I've got everything I did last video. So, the modulus of the entire function. All of sine x is modulated. And for this, we can do the exact same that we've been doing before. We can break it down to its bare essentials. And the bare essentials of this graph is it is a sine x graph. So I can sketch, and this is going to be horrible, but I can sketch a sine x graph. I'll just do one permutation of it. And now I can think about transforming it. So I've got my sine x. So I've got my f of x equals sine x. And now I want to go about transforming it using this modulus. Well, just because it's a sine doesn't mean it's anything different. It's still, lines on a graph. And from last time, we realized that when the whole thing has a modulus around it, we need to take whatever is below the x-axis, so that's all the way from here to here, and we need to flip it. Yeah? We need to flip it. So I'm going to draw it on the same graph here. I'm going to flip it, and I'm going to end up with a graph that kind of looks like some mounds in a hill, maybe. It'll look like that. Keep going like that. Obviously, it'll be a bit neater, but this is the general idea of what it's going to look like. Same for cos, right? Cos is the same graph. It's just shifted over by 90. So when we draw a cos graph, it's also going to look like this. It's just going to have different intersection points on the y-axis. Okay, then what about fx equals sine of the modulus of x? Well, this is what we just looked at. So once again, at the bare basics, this is a sine graph. It is a sine graph with a transformation attached to it. So let's start off by drawing our sine graph again. And actually, I need my axes in the middle for this one, don't I? And I will draw my sine graph like that. Doesn't really matter on that side. Draw my sine graph like this, and then ask myself, okay, how do I deal with it when only the x value is being applied with the modulus? Well, I take whatever is on my positive side, which is all of this stuff over here, and I reflect it in my y-axis. So once again, you should be doing this on two separate graphs, but I'm just going to rub it out here. I'm going to rub out everything where I've got an x that's negative, and I'm going to reflect my sine graph in the y-axis. And this is what this graph looks like. It kind of looks like in the middle, like a McDonald's M. Yeah, we'll go with the McDonald's M. And then from there on out, it will just continue looking like a sine graph on either side. So if you were asked to do this between 0 and 360, well, in that case, it's going to end up being a little bit longer. In fact, I don't even have the room. But it will just keep going like that forever. Once again, don't be scared of it coming onto the negative side. It's supposed to do that, but we are prioritizing whatever is on the positive side and then reflecting that. Right, let's have a look at one more example that puts all of this together. Okay, let's have a look at this kind of thing. So this shouldn't look too scary. Based on what we've just done, we already know what this thing's going to look like. And based on what we did last time, we know how to apply these transformations. So let's go through this slowly. Once again, we want to boil it down to what is the basic function here. Well, the basic function, step one, it is a sine graph. Now, in the last examples, last video, it was always a y equals x graph, but this time that's not really going to be useful. We know that this is, at its core, a sine x graph. So, if we've got this sine x graph, let's start off with that. So, my first port of call is just going to be to sketch a sine x graph. And I'm falling into a very bad habit here of not doing anything on the left of the y-axis, which hopefully we know by now I should be doing, so make sure you don't fall for that. Now we need to work out what transformations are being applied and what's happening first. Well, firstly, my graph or my x values have a modulus applied. That's the first thing that's happening. So my next thing should be to apply this first transformation as follows. So as we just did last time, it's going to stay the same on the right hand side, and then on the left it is just going to reflect, and that is my sine of modulus x. And now I want to apply my other two transformations. So I'm just going to rub out this side because unfortunately I don't have much room. And realize that my next transformation, well, what's happening to it next? Well, it's being multiplied by 3. And once again, from our knowledge of transformations, 3 is outside of the x, it's outside of the function, so we are going to be applying it to the y-axis. So all of my y values are going to increase by 3, multiply by 3. So I'm still going to be at the origin, because 0 times 3 is still 0. But now, instead of hitting a maximum of 1, I'm going to go all the way up to a maximum of 3. And this is just going to look like a bit of a squashed in sine graph, as we should know from multiplying by an integer to the y coordinate. Okay, and now the very last thing is, sorry, it's a bit messy here, is I need to add 2. Well, it's outside of the x, so I'm applying it to my y, so I'm adding 2 to all of my y coordinates. I'm just going to pop it down here. So my whole graph is going to shift up by 2, and I'm going to end up with something that looks like that. Just hopefully a little bit more precise when you do it.